Did you know that a mere 1.2 millimeter difference in pipe wall thickness is often the only thing standing between a successful operation and a catastrophic explosion in a high-pressure refinery? Many junior engineers choose a pipe schedule by simply looking at a table, without understanding the actual physics or the code requirements behind it. That is a dangerous way to design. In this video, we aren't just going to calculate wall thickness according to ASME B31.3. We're going to understand why pipes are sized the way they are and how to choose the right schedule to ensure your project is both safe and cost-effective. Stick around until the end, because I'm going to reveal the 12.5% error that even senior engineers often forget to include in their design reports, an error that could literally invalidate your entire calculation. Today, we are breaking down the 3 pillars of pipe design, the real difference between NPS, DN, and schedule, the ASME B31.3 master formula for internal pressure, the corrosion and manufacturing tolerances that save projects from failure. Let's start with the basics, but let's avoid the obvious. Why does a 2-inch pipe not measure 2 inches on the inside or the outside? It's a common frustration for newcomers. Understanding NPS, nominal pipe size, and DN, diameter nominal, is the first step to avoiding massive procurement errors. This is where the schedule comes in. Think of the schedule as the strength of the pipe. As the schedule number increases, from SCH40 to SCH80, all the way to SCH160, the outside diameter, OD, stays exactly the same, but the wall thickness grows inward. Imagine you are designing a high-pressure steam line. If you keep the same OD, but increase the thickness, you are reducing the flow area, but you are significantly increasing the pipe's ability to contain that internal pressure. This is pure material engineering. Now, grab your codebooks ASME B31.3 and turn to paragraph 304.1.2. We are going to dissect the master formula for thickness under internal pressure. It looks intimidating, but let's break it down together. P is your internal design gauge pressure. D is the outside diameter of the pipe. S is the allowable stress for the material at your design temperature. This is where your choice of stainless steel versus carbon steel changes the entire game. See that little y in the denominator? That is the coefficient factor. It depends entirely on the material type and the temperature. If you use the wrong y value for a high-temperature system, your wall will be too thin, and the pipe could fail due to thermal creep. Later in the video, I'll show you the exact table to ensure you never pick the wrong one. The thickness we just calculated using the ASME formula is the minimum required thickness. But pipes don't live in a clean laboratory. They live in harsh field environments. This is where tolerances come into play. First, we have corrosion allowance C. If your process fluid is aggressive, you must add that extra millimeter or 2. If you ignore this, your pipe will reach its structural limit long before the project's life cycle is over. And here is the secret I promised you: the mill tolerance. Pipe manufacturers are not perfect. The ASME standards allow the actual wall thickness to be up to 12.5% less than the nominal thickness listed in the catalogs. If your math says you need a 10 millimeters wall and you buy a 10 millimeters nominal pipe, you might actually be receiving an 8.75 millimeters pipe. To be safe, you must always divide your calculated thickness by 0.875. This small adjustment is the mark of a true professional. Let's do a victory lap of what we've mastered today. We defined the nominal size, applied the ASME B31.3 formula while considering material stress and temperature, and finally, we accounted for corrosion and mill tolerances. Your design is now bulletproof. One last piece of expert advice: when your calculated thickness falls exactly between 2 schedules, always choose the higher one. The extra cost of the steel is negligible compared to the massive cost of redesigning or failing a hydrodist because you didn't leave enough safety margin. If this level of technical detail helped you today, hit that like button and subscribe to join our global community of engineers.